Alright, welcome. In this video, we're going to be talking about sum and difference identities for trigonometric functions, and to a lesser extent, double angle identities. And I'm not going to be proving those identities for you in this video. If you're interested, then I've already recorded those proofs. You could probably click, in this general area to be taken to a video where I'm going to prove all those things. But for this one, we're just gonna use them. Okay, and so the formulas for sine of a plus b, like two different angles added together inside sine, and you can see them there. You don't need me to read them out to you. And then there's the other one for cosine. What we're going to do right now is kind of like maybe combine these into a single formula, and maybe talk about how we might try to remember it. So, for the first one, sine of a plus or minus b. Okay, notice that both of them it's sine a cosine b, sine b cosine a, and okay, that's probably something you're just going to need to remember, is that sine is the one where it's like a mix of the two functions, sine and cosine. Okay, but, every time it's sine A cosine B, and the other one's sine B cosine A. And notice that the sign, like the plus or the minus between the two things, is the same as the plus or minus originally. Okay? So we're going to say it's the same plus or minus there. Okay, and for cosine, notice both of them, it's cosine A cosine B, and sine A sine B. But with cosine, angle addition and subtraction, the plus or minus afterwards is the opposite of what it was before. So we're going to symbolize that with kind of an upside down minus or plus, okay, indicating that it's the opposite of whatever it was on the other one. Okay, and these formulas are two formulas that we are just expected to know for AP Pre-Cal. And I know it seems like a lot, but if we work with them and we use them and work the homework, you're going to be fine. You'll be able to remember it. Alright, so let's use these formulas. So one thing we're going to do, and probably the main thing we're going to do with these formulas, is evaluate trig functions at unit circle locations that aren't exactly the ones we're used to, like 23 pi over 12. So we're going to use the fact that 23 over 12 can be written as 5/3 plus a fourth, or 23 pi over 12 can be written as 5/3 pi plus 1/4 pi, to find the value of sine of 23 pi over 12. So we're going to need to use the addition formula for sine, right, because we're going to add inside the sine. Okay, and so I'm just going to bring that in from what we had before. And then I'm going to say, all right, well, sine of 23 pi over 12, I'm going to compute that by thinking of the 23 pi over 12 as sine of 5 pi over 3 plus pi over 4. And so I'm going to just, kind of like designate these as my A and my B. Okay, like 5 pi over 3, that's going to be red, that's going to be A, and pi over 4 in blue will be B. And then I'm going to need a trig diagram for each of those angles. 5 pi over 3, a pi over 3 reference angle in the fourth quadrant, and pi over 4, which would be a 45, 45, 90 in the first quadrant. Okay. Now, when I go to apply the formula, I'm just going to, wherever I see A, I'm thinking about the red triangle, and wherever I see B, I'm thinking about the blue triangle. And so I've got the formula, I'm ready to go. I'm just going to say, all right, this equals, and it's going to be sine of A is going to be sine of 5 pi over 3, cosine of pi over 4. Okay, now it says plus or minus, which is the same plus or minus there was before. So this is going to be, I look back to see, okay, I was adding on the inside of the sine, so it's going to be sine 5 pi over 3 cosine pi over 4 plus sine of pi over 4 times cosine of 5 pi over 3. Okay, and then I'm going to, actually look these values up from the trig diagram I drew, looking at the triangle, sine of 5 pi over 3, that's the vertical leg on the red triangle, and it's going to be negative root 3 over 2. Okay, multiplied by cosine of pi over 4, and then I'm going to add sine of pi over 4 multiplied by cosine of 5 pi over 3. And then I'm going to just, from here, just kind of be cleaning up the numbers, simplifying my answer. But, if I multiply square root of 3 times square root of 2, that will be the square root of 6. Negative square root of 6 divided by 4. And then I'll add to that square root of 2 divided by 4. And then since those have the same denominator, I could combine them with a common denominator and say this is negative root 6 plus root 2 divided by 4. And you'll see that's not a surprising answer with this type of problem. It's almost always some kind of combination of root 2 and root 6 divided by 4. Okay, I think that process is repeatable enough that you can try this on your own now. So we're going to do a subtraction. Now it's going to be pi over 4 minus pi over 6, which gives you pi over 12, and we're going to try to find the cosine of pi over 12. Okay, what you're going to need is the cosine formula, so bring that back in for you to look at. Cosine of A minus B is going to be cosine A cosine B plus sine A sine B, right? Because that means it's the opposite plus or minus from what we had before. Okay, so I want you to try to compute cosine of pi over 12 on your own. Do that with video pause because I'm just going to bring in the answers here in a couple of seconds. All right, there you go. So you can see this one worked out very similarly. Root 6 plus root 2 divided by 4. And, even the trig diagrams, it's only so different it can be. And so I think, there's a good amount of practice on this on the homework, on the practice problems. So I think we're ready to move on and talk about the double angle identities. All right, so I think the last of the identities that we have to know for at least trigonometry in this class are going to be the double angle formulas. And we're going to develop these using the angle addition identities that we just learned about and just plugging in x for both of them. So we're going to find an expression for sine of 2x and cosine of 2x. And we're going to need our angle addition formulas. But once again, so I'll bring those in and say, all right, for sine of 2x, what I'm trying to do here is take sine of x plus x. I'm just going to plug in a equals x and b equals x, and I'm going to think about when this is the plus, so it'll be also a plus between the two terms. So I'll have sine x cosine x plus sine x cosine x again, and so that's going to give me two total sine x cosine x's, and it'll be sine of 2x is 2 times sine x times cosine x. And then I'm going to do the same thing for cosine. I'm going to say, all right, well, I'm trying to find cosine of x plus x. And so a and b are both equal to x, so cosine x. And then it's the opposite sign, so it'll be minus sine x sine x. Okay, and if I've got these two things multiplied together, we're going to call that cosine squared x and sine squared x. And we know this looks kind of like a Pythagorean identity, but those are when it's cosine squared x plus sine squared x, and that equals 1, so that's going to be something different. Okay, cosine squared x minus sine squared x, that's going to equal cosine of 2x. And I would say these are also formulas that we're expected to know in AP Pre-Cal. I would say, but if we know the angle addition formulas and we don't know the double angle identities, that's probably not the end of the world because we could just go through this process right here. This wasn't that big of a deal. So one thing we could do with a double angle identity is like solve an equation that otherwise we wouldn't have access to. So we can find the general solution to the equation 4 cosine squared theta plus 2 equals 4 sine squared theta. Okay, so if I was going to solve this anyway, I would suggest putting the cosine squared and the sine squared on the same side of the equation to see if maybe, because we're going to try to apply some sort of trig identity, either the Pythagorean one or this new double angle formula. So I'm going to subtract 4 sine squared theta from both sides. Okay, and then I'll also move the negative 2 over to the other side. Just, if I need to set it to 0 eventually, I can do that later. Okay, but once I see that cosine squared minus sine squared, that needs to activate the double angle formula in your mind. So cosine of 2x equals cosine squared x minus sine squared x. So if I factor out the 4 from the left-hand side of the equation, I'll have something that's equivalent to cosine of 2 theta. Okay, so I can substitute on that and say, all right, now 4 times cosine of 2 theta, that's going to equal negative 2. And I can divide both sides by 4 to get it down to trig function equals number, and that means I'm ready to go to the circle and start thinking about solutions. Okay, so I get a circle out and I think, all right, cosine is negative half, so that's not very far over on the x-axis, right, horizontally displaced negative half of a unit from the y-axis. I was trying to remember the right wording. And so we look around and we see, all right, there's a spot on the unit circle that has that x-coordinate, and here's another spot on the unit circle that has that x-coordinate, and they're supposed to be right above each other, but not my best sketch either. Those are going to be 2 pi over 3 and 4 pi over 3. And so that means that 2 theta is going to need to equal 2 pi over 3 plus 2 pi n, because we're looking for the general solution, or maybe 2 theta needs to equal 4 pi over 3 plus 2 pi n. And then, from there, we're just going to divide both sides of both equations by 2, and just remembering to divide everything by 2, including the, period at which the solutions repeat. And so it'll be pi over 3 plus pi n and 2 pi over 3 plus pi n. And here we go. We've solved an equation using a double angle formula. I've got one more example for you, and this one's got something a little different going on that I wanted to make sure happened at least somewhere in our trigonometry unit. Okay, so I've got sine x cosine x equaling 1/4, and I'm going to ask you to find me all solutions on the interval 0 to 2 pi. And normally we like those because I always have to look one time around the circle, but this one's got a little bit of a wrinkle to it. So what we're going to do, we're going to use the double angle formula for sine, okay, and then for the product sine x cosine x. And in general, when you're trying to solve a trig equation by hand and you have a product like a sine x times cosine x, that is what you want to do, is you want to use that double angle formula and get it reduced a little bit. Okay, but I don't exactly have 2 sine x cosine x. I have 1 sine x cosine x, so I should divide that equation that's highlighted in green by 2, and I get sine x cosine x equals half of sine of 2x. Okay, now I'm in business, so I'm going to substitute the left-hand side of that equation with 1/2 sine of 2x, and then leave the 1/4 the same. And then I'm going to try to start solving, like usual. I'm going to isolate the trig function, so I'm going to multiply both sides by 2 to get rid of the half, and I'll have sine of 2x equals 1/2. And now that I've got it down to trig function equals number, I'm ready to go to the circle and start thinking about solutions. So I go to the circle and think about, okay, sine is a half, so I've got a vertical displacement of 1/2 above the x-axis. And so I'm going to mark that there, and then, put in the spots on the unit circle where I think that is. And if we draw it pretty exaggerated, then we know exactly what spots on the unit circle it's supposed to be. That's going to be pi over 6 and 5 pi over 6. Okay, so that means that 2x is equal to pi over 6 or 5 pi over 6, and I could solve for x by dividing both sides by 2 and getting pi over 12 and 5 pi over 12. And you might think we were done, okay? But if you look at these closely, both of these solutions are less than pi. And so we're looking for all the solutions in the interval 0 to 2 pi. And so where are the rest of the solutions, right? I mean, I guess you might think that that would be all of them, but since we divided it in half, we could really look 2 times through the unit circle and find solutions. And that's what I'm trying to say here, is that we need to, for when it's sine of 2x and we're solving on the interval 0 to 2 pi, we do need to look around the unit circle twice. And if it was sine of 3x, we would need to look around 3 times. So I'm going to go in and be like, okay, maybe I'll add 2 pi to pi over 6. That's adding 12 pi over 6. That would give me 13 pi over 6. Let's go terminal. Okay, so it's going to have the same sign. And then if I divide it in half, I think this is going to work. Okay, but I'll do the same with 5 pi over 6. I'll add 12 pi over 6, and I'll get 17 pi over 6. And then when I divide those in half, I'm going to get 13 pi over 12 and 17 pi over 12. I wanted to get 17 pi over 12. And when I have that happen, look at all of these solutions are on the interval 0 to 2 pi. And you can check it out for yourself. You can take 2x and then, look at these and draw your trig diagrams and see that sine x times cosine x is going to equal 1/4 at these four values of x. So that's going to be all for this example. That's all for this video. Thanks for watching.